Thank you for joining my presentation on the COVID pandemic, treatments, vaccinations, and herd immunity. My name is Terrence Shenfield, and I have been a respiratory therapist for the last 27 years. I am formerly the education coordinator from University Hospital, which is UMDNJ in Newark, New Jersey. I hope you enjoy this presentation, and I think you're going to learn a lot from it. Today's objectives are I'm going to give you a little bit of background on the SARS-CoV type 2 virus. I'm going to tell you about some viral characteristics. I'm going to get a little bit into what they call the cytokine storm. I'm going to tell you some background information on how immunity works. I'm going to talk about some current treatment options, and trust me, this is the third or fourth time we've given this presentation, and each time there's new treatment options as well as new vaccines. So I'm going to cover the most current trends in treatments as well as vaccines, and then I'm going to talk about herd immunity. All in all, you're going to have a lot of good information on the COVID-19 virus. So let me give you a little background on the COVID-19 virus, which really is known as the SARS-CoV type 2 virus. Back in December 2019, there was a huge outbreak of pneumonia cases of unknown etiology that were from Wuhan, China. And at that point, they identified a particular coronavirus family that has not been identified before. This particular virus is part of what is known as the beta coronavirus family, which are typically found in bats and rodents. Now, there's a theory that the coronavirus has come from a laboratory in China, but a lot of evidence is showing that's not true. As much as we like conspiracy theories and as much as we want to read the news and everyone got their twist on it, most medical scientists don't believe that the virus was created in the lab, and most likely it came from either a bat or a bat that came in contact with another animal that came in contact with a human. So that is the basis of where exactly this virus came from. And as of April, the end of April 2021, worldwide, we have about 149 million cases worldwide. So that's an extreme high amount. So I think we could put aside the thought that it came from a lab. It's good conversation piece. But I believe the World Health Organization, is coming out with a study showing that it is not caused by some laboratory, and it most likely came from the bats that came in contact with another animal that came in contact with humans. Let's talk more about virus characteristics. The term SARS stands for Severe Acute Respiratory Syndrome, and basically the SARS-CoV-2 is actually the virus's name, and actually COVID-19 is actually the disease process. Now, they found through some research, and I'll get a little bit more into it in the next slide, that the SARS virus, or the SARS-CoV-2 virus, actually has two different types, and one of them is called L and the other one is called S. And the difference to that is a little bit in the genetic makeup, and actually it's a mutated DNA. And how they could tell by this system called single nucleotide polymorphism, and they found that the L type was more aggressive than the S type. And I'll tell you a little bit more about that. They did a study in Peking University School of Life Sciences, which is located in Shanghai. And what they found that there were two strains. And like I said before, the strains are type S and type L. The type S strain is typically not as aggressive as the type L. And they found that the funny part was that in January 2020, the aggressive strain, which is type L, was starting to diminish. So it initially came out with two strains, and the type S and type L. Type L is much more aggressive than the type S. And as of January 2020, the type L was starting to diminish, and we're having cases of COVID-19 that are not quite as aggressive as it started. So that's kind of interesting. So the type S is located in about 30% of the patients. It is basically a strain that spreads very slow. It actually causes milder symptoms. But the funny part about it, it actually continues to infect patients at a steady rate. So the type S is actually less intrusive, but it doesn't go away. It's keep on going. Where the type L was kind of really aggressive, and it actually caused more illness and actually caused more death. But funny part about that is actually started trailing off as time went on. So that's the difference between the two strains. In regard to spreading of this virus, the primary mode of infection is basically human to human, and it mostly occurs with close contact as a result of droplets coming out of a cough or sneeze. And that is one of the reasons why they're insisting that everyone wears a mask, because if you happen to have the virus and you cough or sneeze, you could contain the particles closer in the mask instead of spreading it around. They also found studies where they looked at the use of face shields, and the virus can actually work its way into the mucous membrane. It could also work its way into the eyes. So you really got to be careful about the transmission of it, and basically it occurs through droplets from a cough or a sneeze. Whenever you see images of the coronavirus, you get this spherical shape, and it has these spikes protruding all around them. These spikes are just not for show. This virus has these spikes for survival. In other words, those spikes fit into receptor sites, and then the virus itself replicates inside the cell. And the receptor that these spikes fit perfectly into is the ACE2 receptor. So you might say, what is the ACE2 receptor? Basically, it stands for angiotensin converting enzyme 2. Basically, this is a protein that sits on the surface of many types of cells in the body, including the heart, the gut, and especially the lungs. It's very important to understand that this angiotensin converting enzyme receptor site is in the lungs, because that's where most of the damage of COVID occurs. The function of the ACE2 receptor is actually it regulates blood pressure, it helps with wound healing, and very importantly, it has a lot to do with inflammation. You may have heard some reports out there that ACE inhibitors, which are used for heart disease, actually created some harm to patients who were taking them. And new evidence has shown that this is not true. They actually did a meta-analysis where they looked at patients who were taking ACE inhibitors, and they found that these drugs are not associated with any severe disease and do not increase the susceptibility of getting the infection. The ACE2 receptor site typically is sitting on the cell membrane, and you might see this ACE2 receptor site in type 2 alveolar cells. And they have found that these ACE2 receptors have little grooves in them. And the sad part is those little grooves take the spikes of the COVID virus, and they fit perfect with each other. So, and once these spikes are attached to the cell membrane, it actually makes copies of itself inside the cell, and that's how it really creates more problems. Patients with comorbidities such as diabetes, obesity, have greater expression of ACE2 receptor sites. So that is why patients with comorbidities seem to have more lethal path with of getting the coronavirus. So this is a little bit about the ACE inhibitors and ACE2 receptor sites. And why I'm saying this to you is because the ACE2 receptor site, some of the treatment options is to block it. So if you block the ACE2 receptor site with some other drug that doesn't harm you, that means that the COVID virus cannot attach to it. And we'll get a little bit more into that later. I wanted to cover a topic in this slide called the cytokine storm. I am sure many of you have heard of the cytokine storm, and basically what that means that our bodies has an inflammatory response and resulting in lung injury, especially ARDS. So let me give you a little background exactly what this is. And most importantly, new research is being carried out to actually decrease the cytokine storm. So if we come up with new pharmaceutical drugs that can actually decrease the cytokine storm, we will have less inflammation, less lung injury. So the immune system has developed a very clever way of recognizing foreign viral particles in the body. And basically, the normal response to any kind of virus in our body is an inflammatory response. But the funny part about COVID has been shown to have an exaggerated response to the immune system. So in other words, the inflammatory response that we normally have to any kind of foreign pathogen in our body is exaggerated tenfold with COVID. Cytokines, which are produced, are an essential part of the inflammatory process. Cytokines are produced by different types of immune cells, including macrophages, natural killer cells, T and B lymphocytes, and so that's how cytokines are produced. During an immune response to a viral infection, our bodies can recognize different viral patterns. What I mean by that, we can recognize the structure of a virus that comes in our body, and when we do recognize it, this activates a inflammatory response. The pathway that does this is called PAMPs, P-A-M-P, and this stands for pathogen-associated molecular patterns. Once our bodies recognize a foreign pattern in our body, this triggers the start of an inflammatory cascade against the virus. What happens is this induces expression of genes that encode different types of cytokines, chemokines, adhesion molecules, and so on. Three of the most important pro-inflammatory cytokines in the body are interleukin-1, tumor necrosing factor alpha, and interleukin-6. Tissue macrophages, mast cells, endothelial and epithelial cells are all major sources of these cytokines during an innate immune response. So the cytokine storm results from a sudden acute increase in circulating levels of pro-inflammatory cytokines, also including interleukin-6, and tumor necrosing factor, and interferon. These increases in cytokines result in an influx of various immune cells such as macrophages, neutrophils, T cells from the circulation into the site of infection. And the problem here, they're all destructive. When they come to the site of infection, they have a destructive effect on human tissue, from destabilization of epithelial cells, also damage to vascular barriers, also damage to capillary membranes, and also diffuse alveolar damage. So as a result of all this, lung injury is one of the consequences of cytokine storm. So that's the real problem with the cytokine storm, is that it induces an inflammatory response, especially to the lung, and this results in an ARDS type of illness. Although we don't know the exact mechanism of ARDS in COVID patients, we all know that this pro-inflammatory cytokines is one of the most major contributing factors. So that's why a lot of research is going into reducing the cytokine storm, and that's why I wanted to give you this background. We're going to start breaking into the topic of immunity, and especially with COVID-19. And quite interestingly, studies have demonstrated that COVID-19 dampens the immune response resulting from impaired immunity. So what I mean by this is that when the virus comes to our body, we don't recognize this right away. And we don't have any kind of mechanism where our bodies would fight off the virus. We don't have any kind of immune response. And the COVID-19 virus has a way of tricking our immunity into thinking it's not there. And resulting is that we end up getting all of these, the virus multiplies in various parts of our body, especially those with high ACE2 expression, such as the lungs. So one of the tricky parts of COVID-19 is it has the ability to sort of slip in our bodies. No one recognizes it. Our body doesn't recognize that it's there. And then all of a sudden it replicates in different parts of our body, especially the lungs, until it becomes a real problem. And then we get this inflammatory response. So I just wanted to give you, they don't really know why this is happening, but they do recognize there's a dampened response to COVID-19. There are two types of immunities in the body. One is called the innate immunity, and the other one is called acquired or adaptive immunity. Each is different, and each is important, especially with COVID-19. When you think about innate immunity, think about this being the first line of defense for the body. In other words, if you digest something into your stomach that is really toxic, you'll vomit. That's an example of the innate immune system. Suppose you breathe in some kind of pollen and you start sneezing or coughing. That's an example of the innate immune system. Suppose that you have some kind of foreign particle in your eye and your eye starts tearing. That's an example of the innate immune response. So the innate immune response also could occur with the production of cytokines, as I mentioned before. So sometimes during the innate immunity response, you will have inflammation. The second type of immunity, which is called acquired or adaptive immunity, is mostly mediated through lymphocytes. And basically, this is the start of building an immunity where vaccines come in important. So, for example, if you get the flu and you get sick and your body mounts some kind of antiviral response to the flu and you build up some kind of immunity and you get better, that's an example of adaptive immunity. So if you ever come in contact with that virus again, your body's going to recognize it and you are going to be able to fight it off rather well. So that's the difference between the innate immunity and the adaptive immunity. And when we get a little bit further into this, I'm showing you how vaccines are part of the adaptive immunity response. The first line of defense for the COVID virus is the innate immune system. Basically, the body has the ability to fight off any kind of invasion from a foreign virus, especially if it's pathogenic. And normally it's done through a process called PAMPs, P-A-M-P-S, which stands for pathogen-associated molecular patterns. And what that means is that the body mounts some form of response to this virus and keep it under control. The problem is the body doesn't particularly recognize the COVID virus. The COVID virus has done a very good job of masquerading itself, so it's not being recognized. And as a result of it, cytokines are released into the body, and actually too much cytokines are released, and that's where you have your cytokine storm, and this actually leads to greater disease severity. So there is a lack of response from your innate immune system with SARS, and that's why you get all as sick as you do. So I wanted to get a little bit into the difference between the innate and adaptive immunity. So some of the key differences, as I mentioned before, is that the innate system is really sort of fast acting. It's like the initial response, the first line of response to any kind of foreign pathogen in the body, where the adaptive immunity is basically a slow immune system, and actually it's mediated by T and B lymphocytes, which develop processes to actually fight off the infection over time. So that's why when you think about getting your hepatitis B vaccine, it works actually through the adaptive immunity system, especially with the T and B lymphocytes. Another type of immunity is called adaptive or acquired immune response. Basically, this is the human body's response to some kind of pathogen that comes into the body, and more importantly, our body remembers that pathogen and builds up a defense. This is the basics of understanding vaccinations. So after the initial infection of COVID-19, antibodies appear anywhere from 7 to 10 days. Mostly the B cells and T cells are the ones involved with the COVID virus, and also they are the ones who actually get this adaptive immunity. What happens is adaptive immunity creates what is known as a immunological memory. What that means is that if that virus ever comes into the body again, the body says, oh, I know you, and it mounts some kind of defense to it. The type 1 helper cells are the dominant role in adaptive immunity with viral infections. They actually secrete interferon and tumor necrosing factor, which are mainly the best tools to actually destroy the virus. Also, cytotoxic T cells are essential in killing the viruses. So adaptive immunity is a very important process in our body. It's very, very important with COVID-19 because that's where all of the vaccines are working from. And our body does mount up a certain defense, but the defense is really not that strong. So our natural immunity, to remember this, is not that strong. So we really need to develop some kind of vaccine. The coronavirus is a very tricky virus. Basically, our immune system doesn't pick up on the virus being in our body, and as a result, we end up being more severely sick. Impaired immunity can lead to virus dissemination and destruction of affected tissues, particularly the tissues that have high ACE2 expression, such as the lungs. The damaged cells can induce pulmonary inflammation, mainly mediated by pro-inflammatory macrophages and granulocytes. Pulmonary inflammation is the leading cause of life-threatening respiratory condition at the severe stage. So basically, because of the ACE2 expression in the lung and the fact that this virus can hide from any kind of dampening or effect from our immune system, we get really sick. So the inflammation suppression is really one of the first types of methods we need to do to actually beat the coronavirus. So a lot of new medications are being presented out there that dampen our immune response so that we don't get this inflammatory process that leads to really severe ARDS. So let's start talking about potential treatment options for COVID-19. As you can see, there's an extensive list here. And the common theme of these medications are to decrease inflammation and also immunosuppression. For example, they have these things called JAK inhibitors. JAK inhibitors are typically given to patients with rheumatoid arthritis. And basically what they do is they decrease the body's overactive immune system. Then what we have methotrexate, which basically is another immunosuppressant drug typically used for immune disease and skin conditions. angiotensin converting enzyme inhibitors like ACE inhibitors. Basically, I told you a little bit about that before, where the ACE2 receptor site seems to be the primary spot where the COVID virus attaches to. So if you could actually prevent the attachment, you will decrease the likelihood of getting a disease. They have shown that patients who are on ACE inhibitors, there's a 40% less chance they will get COVID. Other people talk about interleukin-6 inhibitors, interleukin-1 inhibitors, and that's all part of the cytokine storm. These are all part of the pro-inflammatory mediators, so what they're trying to do is actually reduce these inhibitors coming into the body. So bottom line, they don't want to have as much interleukin released in the system as much as interleukin-1, so they have special medications that inhibit it. And finally, we talk about vitamin D. They actually showed some studies where vitamin D actually suppresses your cytokine storm. So these are all different types of methods that I'm going to get into and different types of medications. And I'm not going to cover all of them because we don't have the time to cover all of them, but I'm going to cover the big ones. So sit back and let's go for it. Let's now start discussing some of the treatment options for COVID-19. Arbidil, which is a medication that is used exclusively in Russia and China, is used as an anti-influenza medication. They did some studies with Arbidil with COVID-19, and they found that it actually decreased replication of the coronavirus in the cell. Basically, what it does, it inhibits the viral entry into the host cell through the inhibition of the viral membrane fusion. They did some clinical trials there, and they used 400 milligrams 3 times a day, and they found that the patients who used Arbidil had less symptoms, less severity, and recovered much quicker. So this is one of the treatment options, but it's exclusively now used in China and Russia, and I think pretty soon we're going to have it here in America. These two medications, chloroquine and hydroxychloroquine, have been in the news recently for the use in COVID-19. There's a lot of political talk about this, whose party is actually promoting it, who's not promoting it, but let's look at the evidence. Basically, this medication is used for the prevention and treatment of malaria and rheumatoid arthritis. It relatively has a safe profile, and it's more considered an immunomodulator rather than an immunosuppressant. So the real benefit of these medications is that it suppresses the cytokine storm. They have done some significant amount of research on this, which the results have turned out to be quite positive. They looked at using this at 400 milligrams per day for 5 days, plus conventional treatment, and they felt that the prognosis of patients who utilized this medication was better than those who didn't. So, yes, it's a safe medication. Yes, I don't care which party promotes it or unapproves it, but basically the evidence speaks for itself, and it's been shown to be quite useful in suppressing the COVID virus. I am sure as healthcare workers, we've heard about the combination of hydroxychloroquine and azithromycin. So the question is, do these two medications put together result in a better outcome for patients with COVID? We know the role of hydroxychloroquine, and it's been shown to be quite effective with COVID, but how about the combination? So they did a study in Brazil. They took 447 patients and they enrolled them in the study from March 28th to May 19th. There was COVID confirmation of 397 patients. The findings in this study was that in patients with severe COVID-19, adding azithromycin to standard care treatment, which included hydroxychloroquine, did not improve the clinical outcomes. So from the study, they do not support the combination of these two medications. You're much better off just taking hydroxychloroquine by itself, where there's some decent evidence showing that it's effective. I'm sure another big medication you have heard about is remdesivir. This medication was first developed to treat Ebola virus. And how it works, it blocks the replication of the coronavirus, such as the SARS-CoV virus, which is the COVID-19 virus. They did a double-blinded study of 1,063 patients where they actually made a control group and a treatment group. And the treatment group received 200 milligrams on day 1, and they followed by 100 milligrams up to 9 days after that. They looked at the results of the study, and they found that the group that had the remdesivir had a shorter time to recovery, less hospitalization, and they had lower incidence of lower respiratory tract infections. So remdesivir does have an impact on COVID patients. It does work with patients, and the evidence has proved it. This is a very interesting study. They actually use what is called therapeutic plasma exchange. Plasmapheresis is the term they used for the exchange of blood. So let me give you a little background. When a patient has COVID and recovers, typically they will have antibodies. And what they did is they did some testing where the patients who recovered would actually get a transfusion and give up some of their blood, and then they would extract the plasma, which included the antibodies. They found that the patients who received this new plasma after 1 week recovered from the COVID virus much quicker than the control group. So at Mount Sinai in New York, they actually tested this on patients who were on ventilators, who were intubated. And they found that the patients who actually got the plasma exchange did better than the ones who didn't. And both of them had conventional treatment for both arms. So this was a very small study, but there's a lot of buzz about it, and it's called therapeutic plasma exchange. And what they're doing is swapping out the antibodies from patients who recovered and give it to patients who are currently sick. Kind of interesting. Many patients with COVID have extreme inflammation of the lungs. And the way to handle that is with anti-inflammatory drugs, such as glucocorticoids. They've done some studies using these anti-inflammatory drugs where what they want to do is actually decrease the cytokine storm. All of the inflammation is caused by the release of cytokines and chemokines. They want to control it. And basically, they want to control the pathways where the inflammation occurs. And they have some pretty promising studies with the use of hydrocortisone given early in the treatment of COVID. So patients who in early stages of COVID get hydrocortisone, and they find that those patients actually recover a lot quicker than patients who didn't. So there is actually a role for this in the treatment of COVID. My last slide is going to be talking about Ayurvedic medicine. I don't know if all of you know about Ayurvedic medicine, but Ayurvedic medicine is what they practice in India. And it basically is a 5,000-year-old medicine, mostly dealing with herbal medicine, meditation, and mind-body techniques. So one of the herbs they use for COVID it's called Gucci Ganvati. Now, I don't know if I'm pronouncing that right. It's Guruchi Ganvati, and they gave that to patients who had COVID. They gave 500 milligrams twice a day to them after meals for 28 days. And they found that the group that received that actually did much better than the group who didn't. So actually here we have a natural form of medicine based on plant therapy, and they had some positive results with it. Kind of interesting. So let's now delve into the topic of vaccines. What exactly is a vaccine? A vaccine is a treatment that is actually given to a patient, and typically it could be the live virus, it could be the DNA snippet of it, it could be the messenger RNA snippet of it, but basically they either give a live virus or a dead virus, And the goal is to stimulate your immune system to remember that virus and build up antibodies. The antibodies that are built up are from lymphocytes, your B cells. So your B lymphocyte cells actually remember what the virus is, and then when the virus actually comes into the body from another method, it remembers that and it'll build up a resistance to it. There are a whole bunch of different types of vaccines, and there's a whole bunch of research being done. There are whole virus vaccines, there are recombinant subunit vaccines, there are DNA vaccines, and there are messenger RNA vaccines. All of them are effective. Each of them have their strengths and weaknesses, which I'm going to go over. A very common vaccine type is called live attenuated virus. And what that means by the word attenuated is that they manipulate the pathogenic features of the virus so that it doesn't make you sick. The advantage of these type of live viruses is basically it induces a very T and B cell response, so it really works on both types of immunities. Site-directed mutagenesis can be tailor-made. The disadvantages, it can make you sick. And typically the processing of live attenuated virus is what is known as cold chain. And some people are sensitive to these live viruses, such as infants and immunocompromised and elderly people, so it's not suitable for everybody. But I would say a live attenuated virus on most people can work very, very well because it induces excellence in induction for both T and B cells. Another type of vaccine is called the inactivated vaccine. And basically this is made of dead viruses. And they call this actually fractional vaccines. What they do is they take the live virus and they kill it with either heat, radiation, or chemicals. And when they kill it, that means that virus cannot cause disease. The advantage is it could still induce an immune response in the body, which is pretty good. It preserves the natural virus structure. It can be rapidly developed. It can be formulated rather easily. One of the disadvantages of this is it can cause sometimes hypersensitivity and may require multiple shots. When you think about it, they're not very cost effective because what you have to do with this type of vaccine is you have to go through a series of shots in order for it to work. And there's a little bit of a T-cell bias with it, which is another problem with it. There are various vaccine types, and one of the major ones is called the DNA vaccine. A DNA vaccine type is actually a genetically modified plasmid. And you might remember plasmids from your physiology class, but a plasmid is a little snippet of DNA, and they actually inject that into the body. And what that is, the body all of a sudden recognizes that and builds up antibodies to it. It has a strong reaction to induce both B cells and T cells, which actually builds up immunity. So it's really advantage because they could easily design it. They could actually manipulate it through different DNA sequencing, making it mostly effective, and it induces a broad range approach to both B cells and T cells. The disadvantage is that sometimes you might have a lower immune response compared to a live vaccine. So this is basically just a snippet of DNA. It's not actually a live vaccine, and as a result you get a little bit less immunity, but it does work. Another vaccine you should know about is messenger RNA. And this particular vaccine is what is Pfizer and Moderna vaccines are produced from. And there are several advantages of the messenger RNA virus. For number one, it will teach the cells how to produce a protein that will trigger an immune response. It also, that protein is actually the same protein that is found in the COVID-19 virus, but the benefit of this is that it has no live or dead particles of COVID-19. It has no DNA, and the benefit of this is that you're not exposed at all to the COVID-19 virus at all, so you won't get sick. It has a great induction of both B and T cells. There are one particular disadvantage of this. This messenger RNA vaccine is very unstable, meaning if it comes up to room temperature, it could be destabilized. So you really need to require to store it at -80 for Pfizer and -20 for Moderna. But these particular vaccine type, messenger RNA, is what you and me and probably most of the world has received, and it's commonplace with Pfizer and Moderna. Another vaccine type is called a viral vector. The viral vector can either be a live virus or it could be a dead virus. But if it's a live virus, they have the ability to manipulate the DNA that virus cannot cause any harm. No matter what, it creates an excellent immune induction in the body, and it primes the body with antibodies to fight off any kind of infection. The disadvantage is inoculation routes may produce different immune responses, and also there is a T helper cell bias, where most of the immunity happens only to T helper cells and not other cells, which can represent a problem. Another type of vaccine is called a subunit vaccine. And you may be asking, what the heck is a subunit vaccine? Basically, it's a snippet of protein, most likely an antigen, that has from the virus, and it has a very safe profile. So basically, rather than having a live virus, it's just a snippet of the protein or the antigen of the virus, and it has a very good effect on cellular and humoral immunity. The disadvantage of this is because it's such a small unit, sometimes you have to add additional features to it called adjuvant, and these additional features maybe are not cost effective. So a subunit vaccine is a very common vaccine, most likely a snippet of protein from the antigen of the virus. So let's start our conversation about the vaccines that are here in the United States. Me personally, I received the Moderna vaccine. The Moderna vaccine actually teaches our body or tricks our body to produce a protein that will produce an immune response. It works by messenger RNA, and basically the likelihood of you getting a COVID disease from the vaccine is nil. It cannot even happen. Typically, you get 2 shots, which are separated by 28 days. The efficacy of these particular vaccine is about 95%. Personally, I had no side effects. It's really been well tolerated. So those are one of the choices, Moderna. Before Moderna hit the market, Pfizer was already being used. Again, Pfizer is a messenger RNA vaccine, and like the Moderna vaccine, it tricks the body to produce a protein that will trigger an immune response. This vaccine has shown no side effects in regard to getting sick with COVID, but some people do get some side effects with, sore arms and such. Again, this vaccine requires 2 shots. Typically, they're 21 days apart, which is a little less than the Moderna vaccine, and it shows a 95% efficacy. So Pfizer is a well-tolerated vaccine that is used for COVID-19. The final vaccine we have here in America is the Johnson & Johnson vaccine. The difference between the Johnson & Johnson and Moderna and Pfizer is that this is a viral vector vaccine. And basically what it does, it's a modified virus that will deliver a genetic code for antigen. So what happens is this modified virus actually triggers an immune response in the body. And this immune response is pretty pretty powerful. It has a 72% effective level. It also has only required one dose, and there's no chance of you getting sick. Um, there was some reports on the market where people were having some clotting issues and it was taken off the market, but the likelihood of getting it is like 1 in a million. So I think this was an overreaction on everyone's part. If you have 1 in a million reactions, I don't think it's that severe. But whatever the case, it's on the market, it's back in play, and it's quite effective. And if someone could get this vaccine, uh, it's better to have 72% coverage versus no coverage. So it's a good choice. No discussion would be complete unless I tell you about vaccines that are used around the world. Let me just start off saying that China and Russia developed an effective vaccine before the United States came to market. In other words, before Pfizer and Moderna started giving inoculations to patients, they already had a vaccine they were giving to people. For example, in China, they developed two vaccines called Sinopharm and Sinovac. Both of these vaccines are inactivated dead viruses. They inoculated over 243 million people, and it's 79% effective. In Russia, they have a vaccine called Sputnik 5. And this vaccine is a vector vaccine. Again, it's 79% effective. And as of March 2021, there's about 3.8 million people inoculated. And the final vaccine that was used in the United Kingdom is called the Oxford's AstraZeneca vaccine. And again, this is a DNA vaccine. It was given to approximately 35 million patients in the United Kingdom. It's 76% effective, but just recently they've been showing reports of blood clot issues and bleeding issues, and they've taken it off the market. This information just came in May of 2021, and it may have changed by now, but these are the vaccines that are being used around the world. And like I said before, China and Russia already had the vaccine on the market prior to Pfizer or Moderna. So that's the end of these vaccines. So you may be asking, exactly what is herd immunity? Herd immunity occurs when so many people in the community have become immune to the infectious disease, in this case, COVID-19. So many people in your community, in your city, in your state, in your country have been infected with the disease and now built up some form of immunity. It can happen in three ways, and you need to understand these three ways. You could be not immunized, but still healthy. So that means that you are a healthy person, but you haven't been in contact with anyone who is sick and you did not get the vaccine. The second group is you're immunized and healthy. That means you encountered a sick person and got better or received the vaccine. And the final group is you're not immunized and you are sick and contagious. So these are the three groups you need to know about herd immunity. Remember, if you're not immunized but you're still healthy, that means you didn't come in contact with anyone and you just didn't get the vaccine, and you are still likely to get sick. If you did get the vaccine or you got sick and recovered, now you are immunized and healthy. And if you are sick and contagious, you are not immunized yet because you're still in the process of being sick. You need to recover to gain immunity. So with these three items, we're going to talk about some graphical pictures that explain it a little bit further. To understand herd immunity, you need to understand the RO value. And I want to explain exactly what that is. The R number is a key factor in gauging the corona pandemic. It actually refers to the effective reproduction number of COVID-19. R refers to the effective reproduction number, and basically put, it's a way of measuring an infectious disease capacity to spread. The R number signifies the average number of people that one infected person will pass the virus to. A concern is that the R value is not fixed, but can be affected by a range of factors, including just how infectious a disease is, how it spreads over time, how the population behaves, and any other condition such as where you live. Is it a densely populated city, or do you live in a rural area? People who live in a densely populated city have a higher RO value. Typically, the RO value today for COVID nationally is each person can spread the disease to 2.2 to 2.6 people. And the incubation period is anywhere from 2 to 14 days. So that's a little background of the RO value. It's very good to understand what this is, because the lower the R value, the better it is. The higher the R value, the worse it is. So let me go through a couple of different images to actually show you how herd immunity works. As I was speaking to in the previous slide, you have three basic types of people. You have those who are not immunized and are still healthy. So they represent the blue people. So blue people are healthy. They never came in contact with anyone with the disease, but they're not immunized. The golden people are people who are healthy. They either are healthy for two reasons. Number one, they either got the vaccine or they got sick with the COVID virus and got better. And the final group is our red group, which is the worst group. They are people who are sick and contagious, but they haven't gotten better, so they have not built up an immunity. And this is the worst case scenario. So let me show you a little bit how this would work. The people in the red represent sick people who are sick and contagious, and the blue people are people who are healthy, who never came in contact with disease. So as you can see from this top graph right here, you have two sick people who are in red, and they are in contact with a bunch of healthy people who never got sick before. And as a result of them coming into contact with them, you end up with this kind of picture where many people could become sick. So now these two people actually made everyone on the right sick, and there's only a couple of people who are not healthy. So here's the second scenario right here. The second scenario is, again, you have two people, right? Two people who are sick. But you have actually 5 people who came in contact with the virus before and got better, as well as might have had the vaccination. And on the blue people, so as you notice, because more people have been immunized and they actually got immunized either being sick or vaccine, less people are sick here. So you have less red people who are very contagious and very sick. And these are the people who most likely have a high mortality. And finally, we get into a perfect group of herd immunity, where you have 2 people who are contagious and sick. You have a bunch of people who have either been vaccinated or they got sick and got better. And then you have a smaller amount of people who actually never got sick. So the likelihood of them getting sick now over here is very, very low. So the more people who are vaccinated, the more people who got sick and got better, the less likelihood it's going to damage the population. And that is one example of how this works. I wanted to give you another graph so you really get a good handle on this. The real benefit is when most of the people in the population either become vaccinated or immunized, the likelihood of spreading the disease to people who did not get vaccinated is lower and lower. So the advantage of herd immunity, I mean, there's a little bit of a double-edged sword there. People who get sick and get better are actually better for the population at large. So let me give you another example. The blue people are healthy people. Those are the people who never got sick, but they never built up any kind of immunity. The golden people are people who got sick, who got better and built up an immunity, or they were vaccinated. The red people are people who are sick and contagious, did not build up an immunity, and are very contagious and sick. And when they get better, if they recover, they will be the golden people. But if they don't recover, there's a potential for death. So the red people represent the people with the highest morbidity. So here we have a population on the left, right here. This whole group of people right over here on the left. And as you could see, we have two people who are sick and contagious in the population. The good part is we have a bunch of people in the golden people who've been sick before or been vaccinated before, so the likelihood of the red people spreading the disease through them is very, very low. And then we happen to have 4 blue people. 4 blue people means that they've never been sick, but they can get sick. And if you notice, this blue person right here only comes in contact with people who've been immunized, people who had either vaccines or they got sick and got better. So this blue person will not get sick. But people in direct contact, like when red touches blue, that is where you get sick. So as the population expands and more people get sick and get better or get a vaccine, the likelihood of these people, the red people who are contagious and everything like that, spreading to blue people is very, very low. So they only could spread to people who are immunized. So probably the population as a whole is much healthier because they don't come in really contact with anyone. And anyone who does come in contact with a really sick or contagious patient actually has immunity. So this is another key advantage of this system. This is my final slide on herd immunity. We all have heard of it. Many people in our country have gotten the vaccine. They either got the Moderna, or they got the Pfizer, or they got the Johnson & Johnson. And many people in our country have been sick with the coronavirus and recovered. As a result, they have a natural immunity and they did very well. So the perfect scenario would be this upper left graph right here, where all those little dots represent people with immunity. Immunity can come from either the vaccine or it could come from the fact they've been sick and recovered. So the likelihood of them coming in contact with another person, let me rephrase that. The likelihood of a person who did not get the vaccine, who did not get sick, come in contact with someone who is sick is lower and lower. So this is the benefit of herd immunity. When we get to this point, you hear a lot of stuff in the news now about when are they going to lift all the sanctions going along with this, and maybe it's based upon this kind of study. So right now you'll have a deeper understanding why the CDC and why they're saying everything should not be lifted, and it's still a political game amongst everybody. But I wanted to show you some of the hard-hit cities. For example, New York City, London, Madrid. They all got hit real hard because they initially started with this type of profile. And this profile showed that only very few dark spots, meaning very few people had herd immunity or actually had the vaccine on board or got sick and got better. So as a result of that, you have a lot of people who are well coming in contact with a lot of people who are very sick. And this is what can cause a real outbreak. Obviously, not everyone dies from COVID, but any respiratory therapist or nurse or anyone listening to this will validate that our hospitals were full of patients who are on mechanical ventilations. And so you really got to be careful. So long story short, Herd immunity is a benefit to everybody. You have a deeper understanding how it works, and you maybe have a little bit of appreciation of how the CDC is sort of rolling out when should we lift restrictions and everything like that. It's based on herd immunity. Once we get to a certain R value, then we can lift restrictions. And the upper left corner will represent the ideal graph we want to go to. In summary, I want to thank you all for joining this webinar. And I still say you should be safe. I mean, especially you guys being healthcare workers. Wash your hands, use the proper PPE, avoid large crowds, be smart. And, more and more people are actually getting the vaccine now. They are getting sick and getting better. So the likelihood of you getting sick is becoming lower and lower. There are some people who do not want to get the vaccine, who are adamantly opposed to it, and actually they're going to benefit from the rest of us who are taking the vaccine and those who have gotten sick and gotten better. So for those who choose not to get the vaccine and think it's all a joke, you guys are actually benefiting from the people like us and probably many people in this audience who are getting the vaccine. It's still a problem in the world. I mean, you just got to read the news any day. Here India has the highest amount of deaths ever. And even though I showed a slide on natural medicine before, who knows how they're dispensing, who knows how they're rolling out their COVID strategies. But since it's a problem in the rest of the world, and since we are getting close to achieving herd immunity, we should watch. We should be a lot careful. And I'm not saying be paranoid, but again, just be smart. And I thank you. I wanted to include a list of some references I used for this presentation. This is a short list. I actually compiled a larger list of references. So if anybody wants that full list, I can give it to you. But I want to thank you and hope you enjoyed this presentation and you have a safe day.